There's two different kinds of potential. There's electric potential and gravitational potential. Okay, electric potential is literally what the potential energy or the work divided by the charge. Okay, electric potential is also called voltage. Okay, gravitational potential is just called gravitational potential, but we can call electrical potential voltage. It's in volts. We can write it capital V. It's also the same as joules per coulomb, right? Gravitational potential is just joules per kilogram. There's no like gravity volts or something like that, right? Electrical voltage is defined as the amount of work to get it from infinity, by the way, to where it is, work divided by charge. So let's say you do 12 joules of work on 2 coulombs of charge. Your voltage is 6 joules per coulomb, or 6 volts, for example. Okay. With gravity, it's sort of like work. It's like M. This is sort of like this potential is sort of like G and H all wrapped up, the gravitational field strength and the height of it, right? And it's not something we commonly use, but we're constructing this parallel thing here. So there it is, right? Okay, so basically, electrical potential is how much energy a certain amount of charge has, right? So we're talking about energy here, right? Definitely you want to keep track of the sign. So charge is either positive or negative, right? And you have to be careful about that. Mass is only positive, right? But yeah, there it is, right? So we've got work is in joules, mass is in kilograms. And there's some very strong parallels here, right? So in electrical voltage, right, voltage is a bit like the pressure. So when we start looking at circuits, it's what makes the current. A bigger voltage causes a bigger current. And then at about 10,000 volts per inch, air actually will break down. So when we do the Van de Graaff here, and I do some demonstrations where we make sparks through the air, just think about that. Every inch of air that it goes through is about 10,000 volts of potential, of electrical potential. Okay, let's do a couple examples here. This is a fairly simple concept here, right? So Hans Full does 0.012 joules of work on 630 microcoulombs of charge. What's the change in voltage, right? So the work is 0.012 joules, and that equals, and Q is 630 times 10 to the minus 6th coulombs, right? And then what is the change in voltage, right? Okay, so this is higher mathematics here. I think I just have to divide, right? 0.012 divided by 630 e minus 6, right? So this will be a big number. This is 19, so the change in electrical potential is equal, or the change in voltage, right? We could say voltage as well, is 19.0476 approximately. We only have 2 sig figs. So I guess that's 19 joules per coulomb, or 19 volts, or ta-da. All of these are correct. Ta-da. All right, so let's look at gravitational potential. How much work would you need to move 34 kilograms from a gravitational potential of 12 joules per kilogram to 67 joules for every kilogram? Okay, so let's see. So our change in gravitational potential is 67 minus 12. This is the hardest part right here. I think it's 55 joules per kilogram. So now we're all set. So work is mass times change in gravitational potential. So we're trying to solve for the work. So it's going to be 34 kilograms times 55 joules per kilogram. All right, hold on. This is multiplication. This is a lot trickier. Okay, 1870. So that's 1,870 joules. Notice that kilograms goes the way of the bison. You end up with, that's sad. I should really come up with something else. The way of the passenger pigeon. It goes the way of hatred in our country. All right, how's that? Although, anyway, yeah. All right.